Okay, now that we have talked about natural response, the next thing that we're going to talk about is something called step response. And again, we're going to start with RL circuits. What do we mean by step response? So by natural response, we meant we had a circuit, it was connected to one or more than one sources, and after the switching happened, it's just going to be left with a bunch of passive elements or a bunch of resistors, right? Resistors and one inductor, or resistors and one capacitor, right? Step response means that after the switching, remember, I'm talking about after the switching. After the switching, the inductor or the capacitor, the element of interest, which is an inductor or capacitor in this chapter, is going to be connected to not only just resistors or a network of resistor or just one resistor, but also sources. So like voltage source or current source, but it's going to be connected to some source, right? So before switching, it could have been connected to nothing. It could have been connected to just a bunch of passive elements such as resistors and some other things, or it could have been connected to sources. We don't care about before. The moment that we see that after switching there's a source in the circuit connected to the inductor or the capacitor of interest, then we know that this is a step response. Okay, so that's just about the naming, but let's analyze it, right? So in this circuit, we want to know what is the VT and IT, the current of the inductor and the voltage of the inductor, for t greater than 0. Okay. Similar to before, we need to actually analyze this circuit and see what happens after t equal to 0. But different than before, after t equal to 0, the switch closes and we have a resistor, an inductor, and this time a voltage source. So it's going to be the equations are going to be a little bit different. So if I want to write, but the procedure is very, very similar. So let's start with writing KVL. So KVL tells me that plus Vs minus Ri minus VL is going to be equal to 0. Therefore, Vs minus Ri minus L di over dt is going to be equal to 0. Because the current of the resistor and the current of the inductor are the same thing, I can use I for both of them. Okay, now I need to just simplify things, do the integral, and find the expression, right? So it's going to be basically, if I take the L over L di dt to the other side and then bring the L to the denominator of this side, I'm going to get Vs minus Ri divided by L is going to be di over dt. And then I'm going to take minus R over L, factor that out from the left side of the equation, just because I remember that R over L or L over R was something special, was my time constant, so it might actually help me. So it's going to be, well, negative Vs divided by R plus I is equal to di over dt. Okay, now I'm gonna move dt to the basically keep dt and multiply multiply dt to the left side and then bring whatever is inside the bracket to the bottom of the I. So I'm gonna have di over I minus Vs divided by R equal to negative R over L times dt. Now I can do my integral. So ln of I minus Vs over R. Remember, Vs is a constant value. It's just the voltage source value. I is the only time-dependent parameter here. Ln of this for t0, or from 0 to t, is going to be equal to negative RL times t. Therefore, I can say that I minus Vs divided by R over I at 0. So this one on the denominator is I of t minus Vs over R over I at 0 minus Vs over R. It's going to be to the negative R over L times t. And that tells me that I is going to be equal to, or let's write it I as a function of t. So I t is going to be equal to I at 0 minus Vs divided by R times e to the negative R over L times t plus Vs over R. Okay, I hope this was clear. Try to do it yourself. I massaged the equations a little bit and I didn't show all the steps, but I'm hoping this was simple enough for everyone to follow. Okay, so I got my main equation. I find my current as a function of time after t equal t for t greater than 0, right? Or after t equal to 0 when the switch closes, right? Now Vs is given, R is given, L is given, same as always. The only thing that is not given and we need to still find it is I at 0, the initial condition, right? But this time the initial condition is actually quite simple for this specific circuit. It doesn't mean that for step response the initial condition is going to be simple. We're going to see that in the next example, the next slide, that the initial condition could be as complicated as what we saw with the natural response. In this circuit, before t equal to 0, so before t equal to 0, well, I just have an open circuit, so there's no current. IL is 0. There's no current passing through this. It doesn't matter that it's been there for a long time. There's no circuit. There's no current passing through any of these components, so that includes the inductor. So IL is going to be 0. Therefore, IL at 0 minus is equal to IL at 0 plus is going to be equal to 0. So for this case, I0 is 0, but then for other cases, we might actually have something different. Okay, so that's the first thing. The other thing is that, similar to before, let's actually look at this, forget about the math, look at this a little bit more intuitively. So it's still about the math, but then we want to see what is the behavior of my current. So if I look at this expression, or the simplified version of it. So let's write it. IT is equal to, or well, not simplified. Let's actually look at the general case. So what would be the I at 0? Well, it's going to be I0 minus Vs times R times, well, e to the power of 0 is 1 plus Vs over R. Vs over R and negative Vs over R cancel. I'm going to get I0. Well, not a lot of surprises. I at 0 is going to be the initial condition, right? What about I at infinity? So if I leave this circuit after switch is closed, if I leave this for a long time, what's going to be the current of the inductor, right? Because before, when I had the natural response, I just had an R and an L, and there was no source. So I could imagine that if I leave this circuit forever, the current is going to be 0. It was a decaying exponential, right? But here I have a decaying exponential term, but I also have this other term, Vs over R. So at infinity, I know that I'm going to have I0 minus Vs over R times, this time e to the power of infinity, negative infinity. It's going to be, because, well, t is going to be infinity, negative something times infinity is going to be negative infinity. E to the negative infinity is going to be 0. So this entire term is going to be 0 plus Vs over R. So I'm going to have Vs over R. So this term Vs over R that is repeated here and also here is really the final value of my current. So the current of the inductor is going to be a very, like, we're basically describing the transient behavior of this circuit and the transient current of the inductor, right? So the steady state current after like transient phase is over, after a long time that the switch is closed, I know that my current is going to be Vs over R, right? So basically, what these two expressions are telling me is that the behavior of my current is going to be in a way that I'm going to start from some I0, I at 0, and I'm going to basically, what happens is that I'm going to have an increasing exponential toward another steady state, which is the, let's call it I at infinity. So this is how it looks like. So in this case, for this circuit, the initial current was 0 because, as I said, so we saw it here, right? The initial current was 0. So we start from 0, right? But then as we move forward, we have two terms. We have this Vs over R, and we have this other term that has the exponential function. The Vs over R is the positive side of things, and the exponential function is the negative side. You can think of it as these two are being subtracted from each other. At t equal to 0, the two are equal. That's why I get a current of 0. After that, the negative side is actually becoming smaller and smaller. The positive side stays the same because it's Vs over R. So little by little, I'm approaching to this final value of Vs over R. Okay? Other than the mathematical calculations, I could have imagined that, like, even if I didn't have this expression, this big expression here, if I asked you what would be the final current of this circuit at, like, I don't know, 1,000 seconds or like 10 minutes after the switching has happened, right? Or after 5 time constants of the circuit, right? So after a long time after a long time has passed. Well, you would have thought that, well, when a long time has passed, my inductor hasn't, like, the circuit doesn't have any change. Therefore, my inductor becomes a short circuit. If it's a short circuit, then we really, like, my circuit becomes just basically a voltage source and a resistor. What is the current of that? It's Vs divided by R. So I could have actually, looking at this resistor, I could have actually known that what is my final value. I didn't really need these expressions and then basically plugging in 0 and infinity into the expression to find the initial and final values. I could have just found that from my circuit by using my circuit analysis knowledge, right? One thing that we haven't done is that, well, the VT is also asked from us. So what is the VT? So VT is the voltage across the inductor. So let me actually draw a line to keep things a little bit organized. So VT is going to be equal to L di over dt. That's the voltage of an inductor, and I know when I know the current of an inductor, the expression for the current of an inductor, I would know. I just need to take a derivative of that and multiply that with an L. If I do that, I'm just going to get the voltage of the inductor. So this is going to be L times negative R over L times I0 minus Vs over R times e to the power of negative R over L times t. Okay, and Vs over R is a constant, so when you take the derivative with respect to t, it's going to be just 0. So this is going to be equal to L and L cancel, so it's going to be just negative R times I at 0 minus Vs over R e to the power of negative R over L times t. Since I at 0 is 0, then this is just going to be 0, negative R and negative R cancel. You just going to get Vs e to the negative R over L times t. So the voltage of the inductor, so the current is actually an increasing exponential. The voltage is a decaying exponential. Does that mean it's always like that? No, it's just for this circuit, we did the math and we got this expression. So like the reason that I'm showing these curves is not because I want you guys to remember this or like to memorize any of this. No, we just did the analysis. We found the expression that is basically explaining or like presenting the behavior of the transient behavior of my circuit and the current of the inductor, and then we found the expression for the voltage of the inductor as well, right? So in a sense, the most important conclusion that I could get from this, or I could take from this, is that I could write the expression for this IT without doing any of the KVLs and KCLs. That's the beauty of it. So why? Because this is really I at infinity. This is, well, I at 0. This is again I at infinity. And then I have e to the power of negative r over L times t. So R, L are given. All I need to do is to find the current of my circuit, or the current of the inductor at 0, and the current of the inductor at infinity. If I have those, I don't need to write a single equation. I just write the answer, write the expression for the answer by plugging in those numbers. How do I find I at infinity and I at 0? Well, I just explained it. So for I at 0, we know that the switch was open, so it is 0 in this case. For I at infinity, I assume that the circuit is going to be, so at, I hope I'm going to have enough space here. At infinity, I'm going to have just the voltage source, Vs, and the resistor, right? So, and this is going to be the I. So I is going to be Vs over R. That's why I know it's Vs over R. I don't need to actually plugging infinity into this expression, okay? Remember, you cannot do this for voltage, right? You cannot do this for this voltage of the inductor. You find it for the current of the inductor. Why you can't do that? Because if you find the voltage of the inductor at 0 minus, that doesn't mean that it's going to be equal to the voltage of the inductor at the 0 plus. And there's no other way that you would know the voltage of the inductor at 0 plus. So don't ever try to use anything but current of an inductor or voltage of a capacitor. Once you have this expression, then finding the voltage of an inductor is just a matter of taking the derivative. So Vt is L di over dt. You have I expression for the I. You'll just basically take the derivative, multiply that by L, and it's just basically first year math or high school math, right? You take a derivative, multiply by L, and you have the voltage of the inductor. Okay? We're going to solve an example so that things are a little bit more clear for you. Okay, so let's do an example for step response. So this example is actually very, very important. I picked it intentionally because other than part A, which is asking us the expression for IT, which is basically finding this, the step response for the current of the inductor, there are other parts B, C, D, and E in this example that, well, you don't see it in the other examples that I solved for this chapter. So there are a lot of things to learn from this example, so please listen very carefully. So part A says find the expression for IT, and I being the current of the inductor, right? So this guy. I know that from the previous slide, I know that IT is going to be, I know kind of like the general form of the expression. So we found that out that it's going to be basically I at 0 minus I at infinity times e to the power of negative r over L t plus I at infinity. So what is r over L? So r over L, now the question is that I have two r's. Which one of them I should care about? Well, the one that is going to be connected to the inductor after the switching, right? By the way, I forgot to tell you about this. Like I forgot to actually look at the circuit first and then start actually solving things. So if you look at the circuit, you see that this time, unlike before, we have two sources. We have a voltage source and a current source. We have a source connected to the inductor, a source and a resistor connected to the inductor before switching. So before t equal to 0, the inductor is connected to terminal A, so it's connected in parallel with the 10 ohm and the 8 amp current source. After the switching, the inductor is in series with the 2 ohm and the 24 volts voltage source, right? So before switching, I have a resistor and source connected to it. After switching, I also have resistor and a source connected to it. However, as I mentioned before, we care about after switching to determine if this is a step response situation or a natural response situation. After switching, I have a source, so it is a step response. Okay, so it's just that my inductor, or like later I'm going to see a capacitor, was connected to a source and now it's connected to a different kind of a source, right? So that's why I call it step. I'm going from, like, I have a step up or a step down, but it's a step, right? I'm not like, basically after switching, I don't have a situation where the inductor is connected to just the resistor, right? So this is a step response. That's why I use this general form of equation, that the current of an inductor is going to be the initial value minus the final value times e to the power of negative r over L times t plus the final value. Okay, so when I want to calculate the r over L, I'm going to look at the r after the switching, because that is the before the switching, it's been there for a long time. I'm trying to find the transient response of the circuit right after the switching. That's the question. See, like it says for after t equal to for t greater than 0, right? So R is going to be 2 ohms and L is going to be 200 millihenry or 0.2 henry. So this is going to be really 2 over 0.2. Okay, what is the I0? So I0, for finding that, I need to actually look at the circuit for t less than 0. For t less than 0, I'm going to have this circuit. So I'm going to have this current source. I'm going to have a resistor, the 10 ohm resistor, and the 8 ampere current source. And I'm going to have my inductor. And this is 0.2 Henry. Now, and this is my current I. Now, if I look at this circuit, I know that because this circuit has been there for a long time, so no change for a long time, no change for a long time. And by long time, I mean from negative infinity all the way to 0 minus, just before the switching, right? Therefore, the VL, voltage of the inductor, is going to be L di over dt. The I over dt is going to be 0, so VL is going to be 0. Therefore, L is going to be just a short circuit. Okay, since L is short circuit, all of the 8 amp current is going to be flowing through here, right? So this is going to be 0. Nothing is going to go to the 10 ohm. So here I'm going to have 8 amperes. So because I defined I flowing from top to bottom, I didn't define. The question defined it to flow from top to bottom. So this means that I for t less than 0 is going to be negative 8. That's why it's negative, because it's the opposite of the direction of this current source. So I at 0 minus is going to be 8, which is also, sorry, negative 8, which is equal to I at 0 plus. So that's my initial condition. How about the final condition? So for t equal to infinity, meaning that when I say infinity, I mean a long time. So that infinity sometimes might mean a few milliseconds, right? Depending on the time constant of my circuit. Remember the 5 tau thingy? So if the tau is like 1 millisecond, 5 milliseconds means 5 tau. So 5 milliseconds is really a long time for that circuit, right? So for t equal to infinity, after a long time, I have this battery thingy. So this is after switching. So I have the voltage source and the 2 ohm resistor, the 24 volts voltage source, and I have the inductor, 0.2 Henry, right? Now, after switching and after a long time, again, L becomes short circuit, So I at infinity is just going to be 24 divided by 2 ohms. 24 volts divided by 2 ohms, so 12 amperes. So very simple. By just looking at two very simple circuits, I could find the entire expression for myself. So therefore, IT is going to be equal to -8, which is the initial current, minus 12, which is the final current, e to the power of -10t, which is the R over L times t, plus the final current, which is 12. So this is really equal to 12 minus 20 e to the -10t. That's it. So that's my current expression for t greater than 0. Okay, greater than or equal to 0. Now, part B is asking me what is the initial voltage across the inductor just after the switch has been moved to position B. So this is one of the most common mistakes that really makes me disappointed when I'm marking your test or quizzes, that I see that although I repeated this many times, people think that for finding the initial voltage of an inductor, the initial value of the voltage of an inductor, they just need to actually look at the before switching situation, right? I have repeated this many times that the current of an inductor is the only thing that you can actually count on its continuity. The voltage of the inductor, if you had a voltage of the inductor just before switching to be, let's say, 12 volts, it doesn't mean anything. It doesn't guarantee it at all that after switching it's going to be 12 volt as well, right? So by looking at the circuit before switching, you're going to have zero information about the voltage of an inductor after switching. So the question is, well, how do I find it then, right? Because if it's not the current of an inductor, any other parameter, how do I find it? Well, find the current of an inductor after the switching and try to find the voltage of the inductor from that, right? So for part B, I want VL at 0 plus. What I was trying to say is that this is definitely not equal to VL at 0 minus. So how do I find it? Well, I know that VL is always L di over dt, right? Therefore, VL at 0 plus is going to be L dIL at 0 plus over dt. Okay, so since I have the I expression after 0, which is the answer to the part A, this is going to be equal to L times d over dt of 12 minus 20 e to the power of -10t, right? So now all I need to do is to actually take the derivative. So d over dt of 12 is just, well, 0. L is 0.2, so this is going to be equal to 0.2 times 200 e to the -10t. Now you want it at t equal to 0, t equal to 0 plus. I want the voltage of the inductor at 0 right after switching, so I make t equal to 0. E to the power of 0 is 1. 200 times 0.2, it's going to be 40 volts. So this is going to be equal to 40 volts. Okay. Now, if I wanted to actually look at the voltage of the inductor before switching, just to make sure that, just to emphasize that this is actually the voltage of the inductor before and after switching is not equal, think about it. What was the voltage of the inductor before switching, just before the switching? Well, just before the switching, I had this circuit. And since this circuit was there for a long time, the inductor was a short circuit. So what would be the voltage of the inductor just before switching? 0, because it's a short circuit, right? There's no voltage across it. So before switching, I had a 0 volt. After switching, a moment after switching, I have 40 volts. This is a proof. This is one of examples that proves to you that the voltage of an inductor can change in a moment. It is not continuous. And you can actually see the plot here. We're going to talk about the plots in part E, but let's actually talk about it now. You see that before switching, the black curve is actually the voltage of the inductor. It's actually 0. Right after switching, it jumps up and it goes to 40 volts. And then after that, it's a decaying exponential. See, like this is the decaying exponential. So it's basically 40 times e to the power of negative 10t, and it becomes 0 after a long time. Okay? How about the current of the inductor? The current of the inductor is actually this guy. So before switching, at t equal to 0, we found it to be negative 8, and you can see it is negative 8. That's how we plot it. Right after switching, it's still negative 8. You can see it's continuous. We don't have these kind of jumps, right? So this is an instantaneous change, but for the current of the inductor, you don't have that kind of instantaneous change. So you have a continuous curve, and then from negative 8, it starts to increase exponentially until it gets to the final value, which is 12, right? You can see that. Okay, so now we saw voltage, we have the current. Now part C asks us that how many milliseconds after the switch has been moved, or like basically goes from after t equal to 0, does the inductor voltage equals 24 volts, right? Well, this is really a math kind of a question. It has nothing to do with circuit. So it's asking you that, okay, so we know that the voltage is jumping from 0 here to 40 volts at time 0. And then after that, it's a decaying exponential. So at what time we're going to get to 24 volts? Well, just do the math. So part C, basically we want to say that, well, at 0 we have 40 volts. At basically we know that V of the inductor, VL, for t greater than 0 is equal to 40 e to the power of negative 10 t, right? So now I make this equal to 24 volts, and then just find t. It's as simple as that. So if you do the math, you'll find t to be equal to 51.08 milliseconds. Okay? So part C is really a math question, but this is a kind of a question that you might get, and then it is going to be helping us a lot in something in a future concept at the end of the chapter 7, which is called sequential switching, where we have more than one switch. We start from, like, basically we have a switch A and switch B, and then basically we need to know, so let's say switch A is actually operating at t equal to 0, switch B is operating at t equal to 2 seconds, right? So we need to know what is the current of the inductor or voltage of a capacitor or whatnot is at t equal to 2 seconds. So we need to actually plug in the numbers, right? I'm not going to confuse you right now. I'm just going to basically wait for that sequential switching topic that we're going to discuss next week, and then we're going to explain that, right? But for now, whenever you basically you were asked a question like this, that how many milliseconds is going to take to get to this value, all you need to do is that, well, you have the expression, just find the t that gives you the value that is being asked. Okay. Another form of this would be, what is the voltage at t equal to 1 second? All you needed to do is to actually plug in t equal to 1 and then find the value, e to the power of negative 10 times 40, and you will find the value of the voltage. Okay. So now part D is asking that, does this initial voltage, meaning the 40 volts that we found in part B, does this initial voltage make sense in terms of circuit behavior? Okay, so this is a very interesting question. So it's saying that, well, you found the 40 volts mathematically, but could you actually tell that your circuit is going to have, your voltage is going to be 40 volts in any other way from the circuit analysis kind of point of view? So let's look at the circuit right after the switching has happened. I have this voltage source. I have this 2 ohm resistor, and I have this inductor. 24 volts here, and basically I have this inductor L here. Now I don't care about its value, and it's t, so this is for t equal to 0 plus, right, just after switching has happened. So the question is asking you that, can you tell at this moment what is VL without actually knowing the, basically using the math? Well, if you think about it, the only thing that we know at t equal to 0 plus for sure is the current of the inductor. Again, the continuity is for the current of the inductor. What is the current of the inductor at that moment? It's actually -8, right? So we found it up here. So I have a -8 flowing downward, or like I can say I have an 8 amps going from bottom to top, right? So the current of the inductor is -8, so I have an 8 amperes flowing from bottom to the top of the inductor. So at that very moment, there's an 8 ampere flowing through this circuit. So this 8 ampere is gonna flow through the resistor and the voltage source as well. So if I have an 8 ampere flowing here, I can say that I have a 16 volts here, because 8 times 2 is 16, right? And because I have that, then I can say that KVL tells me that 24 plus 16 minus VL is 0. Therefore, VL is equal to 40 volts. So I could actually find it from the circuit. But this doesn't mean that I actually violated this rule that VL at 0 plus and 0 minus are not equal. No, I still used, if you see it, I still use the fact that I know the current of the inductor at t equal to 0 plus. I still use my current. I still used my golden parameter and try to find the voltage from there. In one method, in part B, I found that voltage from a mathematical way, and in part D, I used my circuit knowledge to actually find that voltage. But in both cases, I used the fact that the current of an inductor at 0 minus and 0 plus are equal to each other, and I just try to actually use that fact to find the voltage of the inductor at 0 plus. So this is at t equal to 0 plus. Okay. I hope this was clear. Part E is just saying that plot both IT and VT versus T, which, well, you have this plot here.